All right. Okay, so let's have a look at how we can abandon these if-then-else rules for some use cases and use instead data to have machines learn patterns and then predict things based on these patterns, and this way automate other use cases that we couldn't automate before. So we will look at different things. So first, let's get an overview of this broad field of AI and machine learning and how they are connected together. We'll see that when we talk about AI, we usually these days mean some form of machine learning, and we will look at how these are connected, and then quickly use the example of rules versus data again, and then look at what types of learners we actually find in machine learning, and we can divide these into supervised and unsupervised learning methods, and we will look at different examples for both. And then I would like to go through what is called by a video 7 steps of ML. There's a video that introduces 7 steps of machine learning that gives us a good overview of what's necessary in order to train a machine learning model for a specific use case. And I want to go and watch that video. It's a short video. I think it's less than 10 minutes, and we'll go look at it in the end. So if you want to define the term artificial intelligence, you will find as often many different definitions for that. And artificial intelligence is a very, I think, special case where there exists many different definitions. And so I don't want to list all of them here. I just want to give you one example, which I think is very broad, and it covers many of the things that we actually do with AI, and it simply says AI is to simulate any intellectual task. So this is very broad. There are definitions that are much more specific to what we mean by artificial intelligence. But if we have this broad definition, and we see on the right side, so what is actually typically subsumed under this term artificial intelligence, if we mean by that to simulate any intellectual task. So these are basically all things that humans with our brains can do well, but sometimes we try to transform a certain intellectual task into our machines because they might be able to do them better or faster or with less errors. So these are all examples for that. So maybe we can go through them really quickly. So if you think about search and planning, so searching in a space of solutions is a very good fit for computers because they can very fast search through large spaces. So a good example is chess. I think everyone knows chess. If you have a chessboard in front of you and you want to know which are the moves that you can possibly make, and you want to do that not just for the very next move, but for next 10 or 20 moves, you get basically a tree of possible moves that you do in the next step, then your opponent is taking his next move, and then you again, and with each move you have different options, and the tree becomes very large. And that's what we basically mean by search space. So the space of possible moves in the example of chess. So we as humans, so I can't think ahead more than, I don't know, 2 or 3 moves, and that's even just a very vast guess, I think. So computers could really precisely think through many moves ahead. So they can evaluate every chessboard and think about what would be the next best move, knowing all the possible moves and being able to evaluate the current state of the board by some function. It can decide which move is likely going to be the best if we want to win the game. So that's basically search. And the idea here is simply, okay, we know all the moves and we can search through them and we can just find the best, or we look ahead a couple of moves, so we don't have to take the whole space into account, and then this should be enough to beat a human player. And this is basically what chess computers do. This is what Kasparov was faced with when he was defeated by a computer in 1997. So this was all about clever searching through the space. And this is what we used to call AI, or still sometimes subsume under AI. So searching and planning, which is basically the same thing or a similar thing, where we also look through different options and see which is best. So then we have another field called reasoning and knowledge representation. Here we try to represent knowledge in some form, so the computer can see if it sees a certain question, and it can then see whether it can connect the question to the knowledge representation and get the correct answer from a database that contains the knowledge representation. And this is there are different approaches to that. And so, for example, Jeopardy, there was a Jeopardy computer that played Jeopardy, which I think it was even Watson from IBM. And that computer basically had a vast database of knowledge that it had represented in some clever way. And based on what the question was, it was able to browse and search through this vast amount of data and try to come up with the right or best answer. And it can do that, of course, very quick. And I think it also beat human players, very good human players, many times in a row. So that's an example which we would also subsume under AI. And then there are other fields like natural language processing, trying to understand speech and text. So have computers understand what is the content of a text, of a tweet, of an online article, try to get the most important information out of the article, see whether the article is positive or negative, trying to determine sentiment, stuff like that. That's natural language processing. And we try to have machines understand that. And then robotics, which is more physical, where we have robots that should learn how to move in space, how to move on a surface, how to pick up objects, for example, pick up fruits that are soft. It's still a challenge for robots, and we want to teach them how to do that. This is a broad field called robotics, and there are many open questions still. And of course, perception, by which we mostly mean vision. So having computers learn to see. So for example, when I see a video and I want to recognize a street sign or a car, in the case of an autonomous vehicle, this is computer vision. And touch, of course, is similar. It's just a different sense. So perception, have computers learn our senses that we use in the real world to get along. So how is this all related to machine learning? And machine learning is the biggest circle here. And that's currently, as I said, I would say 99% of all applications that we mean when we say artificial intelligence are actually machine learning. And this is why we can connect all these fields that we listed here somehow to machine learning. So for example, to solve the problem of computer vision, we employ deep neural networks that can detect images, detect objects in images, and deep neural networks are one type of machine learning algorithm that we can use. Same goes for robotics. To learn how to pick up an object and to move on a surface, we use what we call reinforcement learning, which is also a learning technique from machine learning. Same goes for natural language processing, and even in the classic fields here, search and planning, more and more machine learning algorithms are employed to solve them even better. So this is just the takeaway here. Artificial intelligence, when you read about it in the news or when you talk about this, it's 99% machine learning, and this is what we will call it the rest of the sessions, because that's what we're going to focus on. So when we look at machine learning as its own field, we can look at different ways how we can characterize different types of machine learning. And here's one image that tries to show that we have basically three different types and different types of learners. So how can a machine learn? And there's three types. One is it can learn unsupervised. The other one is it can learn supervised. And then we have a special case, which is called reinforcement learning. So we will mostly deal with the supervised approach, and this is what we'll look at a bit closer. We will also touch on the unsupervised learning, and we won't go any deeper into reinforcement learning. So we will now briefly look at what's typically meant by supervised learning. So when you want to teach somebody a new topic or a new skill, one way you could do it is showing them examples of, for example, I don't know, you want to teach a child how a rabbit looks like. You could show the child images of rabbits and tell it, okay, this is a rabbit. And you could show the child images of which do not contain rabbits and say, there's no rabbit in it. It will quickly learn what a rabbit is. And this is similar to how we teach a machine what a rabbit is. So we show the machine images that contain rabbits and images that do not contain rabbits or that contain other objects or animals. And we have the machine learn by giving it the correct example, and we tell it when it is wrong. So for example, you feed an algorithm an image and it will say, yeah, there's a human in it, but there isn't. We can tell the machine, no, you were wrong. There was not a human in it. And we can basically punish the learning algorithm so that the learning algorithm adjusts its model. So the next time it sees the same image, it will more likely say there is no human in the image. And by that, depending on the learning algorithm that we're employing, gradually the model will be updated so it can then predict what's in an image based on the images it has seen in training. So that's supervised learning. The idea is we have the right answer. We tell the machine, this is the right answer. This is what you said. Figure out the difference. And that's basically supervised learning. And there are two different broad applications that we can find for supervised learning. One is classification. And by classification, we simply mean putting something that we want to classify into certain categories. So for example, image classification, which we just talked about, we could say, okay, we want to know whether there is a rabbit or there isn't. We want to know whether there is an orange in the image or there isn't. So the task of the machine learning algorithm is to say, okay, output 1 means there is an orange, and output 0 means there is no orange. So it could be a binary output. It could also be, okay, we have 10 different objects that we want to classify, and depending on which object is in the image, we want to have either one of the 10 outputs to be on, to say, okay, this is in the image. So we've seen this with the example last week when we tried to have the machine recognize different things like the teddy bear or the toothbrush, and there were some things it didn't recognize. That's because it has never learned to recognize these things and it can't classify them. So basically we need to include everything that we want the model to be able to classify also in the training data and set up the model accordingly. Credit card fraud detection is another field for classification. For example, if you have a transaction, the company or your bank has some data about the transaction. So when it took place, what was the amount, where did it take place, maybe what was bought. And based on this information, it can say, okay, it's likely to be a fraud. So maybe your credit card was stolen or the information was stolen and it's being used somewhere else in an unallowed context. So it can easily, if we have examples of regular credit card transactions and ones that are fraud, we can have a machine learning model figure out what are the indicators for a transaction being fraud. And then we can use that to automate the fraud detection. And that is widely used today by banks. So if you perform, if your credit card was actually stolen and you have a relatively modern bank, you will get informed really quickly if there was something wrong with your credit card, and you will get an update really fast, and they will block the transaction. So that's classification. Diagnostics in medicine, for example, when we have images, again, that show some symptom, machines can learn to recognize and classify images, for example, to say, okay, there is a tumor visible or there isn't. And even very small ones, which are just a couple of pixels, it can learn to recognize. And then the doctor can look at it and gets a hint where to look. And this is a good a good task for machines, because they are very fast, that they don't make any mistakes in this regard, at least if they have a correct model, so they don't miss anything, while humans, of course, can miss based on their status, if they are tired or something like that. And then we have regression as a second field. Regression is the difference between classification and regression is that in regression, we want to predict a continuous variable. We want to predict, for example, our turnover for the next month. That's a variable between 0 and any number as high as we can go. So that's not a set of classes that we want to classify something in. That's a number that we want to predict. So for example, if we want to predict how old someone is, which we also had as an example, that's regression. The algorithm does not give us the indication which class it thinks it is. It gives us a number as an output. And this is basically the difference. And then let's go to the unsupervised learning, where we mainly will look at clustering. And clustering is simply, so first of all, unsupervised learning means we don't have any right answers. So in supervised learning, we have right answers. So for example, for the age prediction, we would have the answer, okay, we know how old a person is, and we have the image, and we can feed that to the machine, so it will learn from many images where we have the right answer to predict the age for images it hasn't seen before. In the case of unsupervised learning, we do not have a right answer, or there isn't even one. So the idea here is we give the machine data, and for example, in clustering, we just want the machine to find clusters that are similar. So for example, we have customer data, and we want to know, okay, which customers are similar to each other. And then after we know that, we just get the information, this is a cluster, this is a cluster, and this is a cluster, and these customers belong to the first cluster, and so forth. But we don't yet know anything qualitative about the cluster. So we don't know what the characteristics really are. So we can then go into analysis and see what they are actually having in common. And so, for example, in customer segmentation, this is a technique that is frequently used to find similar customers with similar things that they want to buy. For example, recommendation engines are based on that. So when you go on Amazon and somebody says, people who also bought this, this is clustering because they know you are similar to somebody else in their database, and they have figured out what these people bought, and they will give you the recommendation what you should buy as well. So customer segmentation and recommender systems are two famous examples here. And then the field of reinforcement learning is a little bit special. It is kind of supervised, but instead of giving a set of right answers, we have an environment where the machine can act, and it will get a feedback from the environment about how good its action was or how useful its action was. So, for example, when we train a robot to move, robot navigation, when it falls, it will get a negative feedback from its environment and say, this was probably something you shouldn't do in the future. So avoid whatever you did before you fell under the current circumstances. And gradually, by giving it always feedback and integrating this feedback into its own model, it can learn on its own by the feedback from the environment to figure out and to handle some tasks. Same as in game AI. So if you for example, have a machine learn a game, it can simply be presented with the pixels of the game, and it can learn what the score is. So we can give it the score, and we've seen the Flappy Bird example where it learns to navigate through the pipes, and it will increase its score over time by just learning which moves it needs to make based on the current pixel state of the screen in order to get more points. And at the beginning, it will be terrible. It will run into every pipe. And as we've seen, after a lot of runs, it becomes nearly perfect at the game. So this is reinforcement learning, which is it's a very promising technique, and some think this is the future of AI, to do research in reinforcement learning and try to tackle more and more problems with that. It's an ongoing and very interesting field. So we are going to start with and mostly focus on supervised learning, because that's the easiest for us to understand, and it's also one that we can get our hands on and do ourselves. So we can train a model with data and create a supervised or a machine learning model that does either classification or regression for us. So we've talked about the difference between rules and the data-based approach. So the question is actually, to what degree was the programmer involved in the decision-making process? So when I have the left side, I have to program all these rules, and here's an example how it could look like for recognizing oranges. So we could have a function that says is bumpy. It's simply a function we would have to implement still, but so we can say, okay, if it's bumpy and it's orange, then say, okay, this is probably an orange, and if it's green and it's smooth and it's an apple. So this is just one example to give you a hint what these rules could look like. Of course, these wouldn't be sufficient still, but it could be a lot of these kinds of rules, and then we might be able to figure out for some images, but definitely if we see a different image, for example, if it's black and white, we run into problems because there's no color orange in it, and we will fail. Our program will simply not recognize it. So what we want to do instead is we learn by example, and we feed a lot of images of oranges and those who do not have oranges into a training algorithm, and we get a model that can then distinguish between them and learn what the patterns of an orange in an image are and how it can recognize them. And there's actually no programmer involved anymore. There's just the data and the machine that is trained, and then it can perform this task on its own, because basically what it has done, it has learned these kinds of rules. So it's basically what the model is somehow a set of rules, but not hard-coded and not it's much more fine-grained. So this is, we just talked about this, so supervised and unsupervised learning. Here, just some terminology. In supervised learning, the training data is what we refer to, what we show the machine. So for example, if we have 1,000 images of oranges, this would be our training data, and we would show that to the machine. And the correct answer in it, so the information, there is an orange in it, that's what we call the label. So the correct answer we call label, and we will see later on that all the things that describe our whatever we want to categorize, our orange, these are so-called features. And on the left side, for unsupervised learning, there is no correct answer. There's just the data, just the features. And let's look at an example for supervised learning that isn't about oranges. So as we just said, the training data consists of features. So these are features. In this case, we have height, weight, and hair length, and a set of discrete labels for classification. So these are the labels. And in this case, it can only be female or male. We could have a third gender. Let's keep it simple. We have male and female here. And we want to classify unknown data. And in this case, a set of features makes up a data record. So when we now have a person and we only know it's her or his height, weight, or hair length, we want to predict whether this person is female or male. Now, we don't want to do it with rules. So we could write, if height is bigger than blah, blah, then it's likely to be a male or a female. And then we take the hair length and have a very specific set of rules that will, with some probability, allow us to predict the right answer. Instead of doing that, we want a machine to learn it. And so we feed it the training data. And the training data consists of features and of a label, the right answer. And then it should, depending on what algorithm we're using with different methods, figure out these rules by itself. And what we then do is we feed it unknown data. So for example, it only sees this, 159, 45, and 51, and then it will predict whether this is a female or a male. And this works quite well for many different use cases, and depending on which use case we have, one model will work better than the other. And we will look at different models when we look at RapidMiner for a data set. And then we will get our hands on supervised learning and get a better understanding of how well it can work in different circumstances and which models we can apply. So this is the supervised learning classification, and then we have supervised learning regression. And the difference here is we have features, so that's the same, and then we have continuous labels. It's not discrete labels anymore. So we have, for example, a price. A price can be any number between 0 and a very high number. And this is basically from a car data set, and we want to predict the price that a certain car, a used car, can achieve on the market. And this could be based on the brand, the year it was manufactured, and the mileage it has currently on its, I don't know what the name is, but you know what I mean. So the training data consists of these rows. Of course, we should have more than 3 rows. That's just an example, but we can feed these features along with the real price that this car has made, for which it was sold on the market, to the machine, and the machine then can learn to predict the prices for unknown data. So for example, if you go to mobile.de and you put in your used car and they ask you for some attributes like your brand, your year, your mileage, but many, many more, then they will give you a suggestion what a good price would be and which you will likely be able to achieve. So they probably use some supervised learning algorithm behind the scenes, which we don't know, but I guess they do. And this is basically what it would do. So it will predict based on all the other sales that it has seen, and mobile.de has a large database of this. And I think there's also a data set that we can download from there. It will be able to actually make a very good prediction. And this is one application that is also being used in practice. So this is regression. And to highlight the difference between regression and classification, so regression in forecasting the weather would be to forecast the exact temperature for the next day. So 84 degrees Fahrenheit in this case. Classification would be, is it cold or hot? And then we would have to somehow decide what is cold and what is hot, but we want in the end only to know from the machine, is it hot or is it cold? Or is it going to rain or is it not going to rain? It's in this case binary. So that's a picture that tries to highlight the difference between regression and classification for the same use case in this case. And then unsupervised learning, clustering is the method that we are going to look at. It's, again, a set of features, but no labels in this case. And what we want to get is a set of clusters from the machine. And these clusters are going to be assigned by the clustering algorithm. And it detects, and there are different methods, similarities in the data. And you can imagine the data is in a high dimensional space. So this is 3 dimensions because we have 3 features, but we can have basically 1,000, 10,000, or even millions of features. And this is then an impossible task for humans, but for machines, it's actually something that can be solved, and they can find in a very high dimensional space points that are close together and form so-called clusters, and then we can get the information about which falls into which cluster, and based on that information, we can do further analysis, or we can build recommender systems, for example. So now we would watch this short video if we have the time. And I think that, yeah, so I think it makes sense because what we will do afterwards, no, I think we skipped the video for that. We skipped the video. You can watch the video at home. It makes more sense this way. So this is just to let you know what's in it. So it's basically one example of classification, and the video goes through 7 steps that you would need to perform in order to set up a model that can do this classification. So it involves gathering the data, preparing the data, setting up the model, training, and so forth. It's a very, I think, intuitive and illustrative video, which I recommend. But you can watch that at home. Makes more sense. Then we save some time at this point. And this is basically also the last slide to introduce the topic of machine learning and especially the different types of learners, which was the focus of this short presentation.